This is our fluid mechanical dissection, where we took apart a 224cc single-cylinder internal combustion engine. While there are many fluid mechanical devices at play in this engine, we chose to focus on the journal bearing and the carburetor. First off is the journal bearing. A journal bearing is a type of bearing primarily used in high load cases. They display exceptionally low wear characteristics because the journal and the housing only contact each other while first starting up and when at rest. While rotating, the oil or lubricant between the components separates and stabilizes the journal from the housing via hydrodynamic forces. But how do they work? As shown in the left image, there's a region where the fluid is quite thin, and the components are nearly touching, and there's another region where they are separated by a larger distance. While the journal rotates, it moves the fluid with it, and the journal processes around the inside of the housing. This moves these regions of lower and higher separation around the circumference of the housing. In order to satisfy conservation of mass at the location with small separation, the flow rate in must equal the flow rate out. Because the Reynolds number here is low, which we will see in the next calculation, the flow is laminar. As such, the pressure increases as the distance between the journal and housing decreases, and pressure decreases as the distance increases. This is what generates the stabilizing force that acts on the journal, pushing it towards the center of the housing. As speed increases, this force is higher due to increasing fluid velocity, and the journal will move closer and closer to center, as shown in the image on the right. An important calculation for a journal bearing is the resistance torque. In this case, we assumed an operating temperature of 40 degrees Celsius and an operating speed of 3,600 RPM. The first step is to calculate the Reynolds number as shown, which comes out to 9.56. Since this is very low, we know the flow is laminar and can be approximated as unidirectional, which allows us to model this as a Couette flow problem, with fluid between two moving parallel plates. We now turn to the Navier-Stokes equation to solve this model, which simplifies down quite a bit given the unidirectional flow assumption. This eliminates all left-hand side terms in the first block, and the gravity term falls to zero since this is a small system. We then make a series of ansatses or guesses. First, that the pressure is spatially uniform, so the grad P term goes to zero. And next, that the velocity is uniform horizontally or equidistantly from the plates, which we will call the x direction, but not as we look at varying distances from the plates, which we call y. This reduces the PDE to the third block, which is solvable by twice integrating and then applying our boundary conditions, assuming the shaft rotates and drives U top and the housing doesn't rotate, so U bottom is zero. Plugging in the values from our engine yields U of y equals 3.06 plus 43,808.16 y. In order to calculate the torque, we first need to find the shear stress from the fluid acting on the wall. The formula is shown here in the second block. Taking the derivative of U of y as shown in the first block and multiplying by viscosity yields 3,329.42 pascals. From this, we simply multiply by the area of the bearing contact surface and then by the radius, yielding force and then torque respectively. This torque is calculated to be 0.105 Newton meters.
Next is the carburetor, which creates a constant stoichiometric fuel and air emulsion at variable throttle levels. We will focus on two key components, the venturi and the float. A venturi is a device that is used to pull fuel into the airflow to mix them. In order to do this, there is an intake side, a throat, and an exhaust. The intake and exhaust have nearly the same cross-sectional area, and the throat has a smaller area. To analyze this, we must first recognize that this is a relatively low velocity system, so the Mach number is less than 0.3, making it incompressible, and it is also steady. Due to the extremely low viscosity of air, the Reynolds number is high, so viscous effects are also ignored. This allows us to use the Bernoulli equation. This is the Bernoulli equation. Given that our system is horizontal, the gravity terms are equal and cancel out. Setting all terms denoted with a 1 to be the intake and terms with a 2 as the throat, we can rewrite this equation as shown in the second block. Due to the conservation of mass, a decreasing area from the intake to the throat necessitates an increase in velocity in the throat, corresponding to a decrease in pressure, which is used to pull gasoline into the airstream. We can link the intake and throat velocity by using the area ratios of the two regions, which allows us to rewrite this equation as shown. Substituting in the values from our engine, we yield a pressure difference that is 0.932 times the intake velocity squared, measured in pascals. As throttle increases intake velocity, the pressure difference increases and more fuel is drawn in. The air and fuel flow are both ideally proportional to the square root of the pressure difference via Bernoulli analysis. This allows this simple fluid mechanical device to mix a constant ratio of fuel and air through variable intake. Carburetors also make use of another fluid mechanical device called a float valve. The float is used to regulate the fuel level in the reservoir the venturi draws from by using the buoyant force to actuate a needle valve. The float obeys Archimedes' principle, which tells us the buoyant force required to actuate the float valve is equal to the volume times density of the fluid it displaces times gravity. This means that when designing a float valve, the ideal fuel level and valve sensitivity can be set by changing the mass, density, or volume of the float. Our float displaces 4.42 grams or 5.94 milliliters of fuel. All right, I'm going to go get a drink of water.